Okay, Year 11, new chapter. We're talking this time about the rates of reaction, or how fast a reaction goes. So I chose these two images just to show some extremes. So we've got an explosion, a very, very fast reaction that produces gases. And then we've got rusting here, rusting of iron, which can take months to years to happen. So just trying to show some extremes. What affects the rate of chemical reaction? Okay, so first we're going to have to talk about speed and the range. Excuse me. Okay, what a terrible start. Some chemical reactions are very fast on the scale of microseconds, so explosions. And I had a GIF there. These are all GIFs except this one, this bottom one. So explosions, some chemical reactions are moderately fast on the order of seconds, so when we see precipitation reactions and such, and some are quite slow on the order of months to years, such as corrosion from before. Some are extremely slow, and the example that I used is the replacement of calcium for silica, which is the process of fossilization. So we're talking about millions of years there. Okay. An example of a fast chemical reaction are airbags. So airbags use a rapid chemical reaction that produces a gas to fill an airbag. So the reaction is the decomposition of sodium azide here, NaN3. N3 single minus is the azide anion. You don't have to learn that. Okay, it's triggered this by an electrical spark, by a sensor in the hood. So you've got a crash sensor further up here, sends an electrical signal out to there, and it triggers this chemical reaction. And look, it produces sodium metal and 2 moles of nitrogen gas to fill the airbag. So it happens in the order of milliseconds in order to prevent serious injury to the passengers. Solids that rapidly react to form gases are usually called explosives, as the volume dramatically increases in a short amount of time. Okay, so there's just a range of times. Let's talk about why chemical reactions happen. A little, not totally. So chemical reactions occur when these two things happen, okay? So for a chemical reaction to occur, the reactants must collide, but they must collide with enough energy to overcome electron-electron repulsion between the two reactants. So when these two molecules get close to each other, there will be a little bit of attraction when they come near to each other, dispersion forces, dipole-dipole and such. But once they come too close, it becomes a repulsive force where the valence electrons and all the electrons want to repel each other and push them away. So the speed must be great enough to overcome electron-electron repulsion and overcome that repulsion so they crash into each other and then they can change, okay? So that condition must be met. There's also another condition. The reactants must be in the correct orientation, okay? Sometimes when two molecules hit, no reaction occurs. Sometimes when they hit in a different orientation, a reaction occurs. Okay, I've got a better diagram up here to show you. Okay, so here I've got an animation which is not working in the PDF, but what I was trying to show you is when these come together without enough energy, they get repelled the same, and they end up just being the green and the white out here. When these come together with a lot more energy, therefore the bigger arrows, what you get is, coming away, you'll get new products forming. So that's the animation in PDF form. Okay, here we go. The reactants must be in the correct orientation or geometry for a successful reaction to occur. So here I've got, I don't know what, nitrogen perchlorate, I'm going to call it. Two molecules of, well, let's just consider, So two molecules of NOCl coming together to form chlorine and two molecules of nitrogen monoxide. Okay, so here I've got an animation. It doesn't work too well in PDF, but here I've got look, I've got three conditions. Here these two are coming together red to red. What am I using for the red? Probably the oxygen. And the nitrogen would be blue and the chlorine would be green. That old convention. Okay, so we got the oxygen to oxygen coming together here. O to O. Here we've got the O coming towards the Cl. And here we've got the Cl of the molecule coming towards the Cl. So different orientations, okay? So let's see what happens. They're getting closer, getting closer. Look, here's where they're meeting, like my little animation there. So oxygen to oxygen, oxygen to chlorine, chlorine to chlorine. Let's see what happens. These ones are just repelled. Okay, so the oxygen to oxygen, no reaction. Oxygen to chlorine, no reaction. Chlorine and chlorine have met to form Cl2 and NO and NO. Okay, so here we go. So in this orientation, no reaction. In this orientation, no reaction. And in the chlorine to chlorine orientation, there was a reaction because Cl2 was formed. So the correct orientation or geometry must happen for a successful reaction. Words. Okay. I think I'm going to call it quits there. Oh no, let's go forward. Yeah, let's keep going. Okay. So some of the things that can affect how fast a reaction happens. The first thing that we're going to talk about is states. So solid, liquid, gas. Okay. So the state of a reactant affects the rate at which a reaction can occur. So reactions can occur when the particles have the ability to collide, and some states inhibit that ability while some enhance it. You can see where I'm going here. So solid reactants are very slow because collisions can only happen on their surface. Okay? Yeah, so our particle model, our particles of the solid are in a nice rigid pattern. So you can only get reactions happening if they're hitting the outside. Okay? Liquids are faster than solids because they can happen at the interface of a liquid. Okay? All around here as well. But the liquid can flow. Okay? And the liquid moves around, so it's a little bit faster. Gases are the fastest as they freely move in 3 dimensions and with a lot of kinetic energy. So there's a lot of chances for meeting something else and reacting. Also, dissolved particles, so let's just think about something dissolved in water, react quickly as they can also move in 3D space like a gas. Not quite as quick, but still very freely. So reactions in the aqueous state can be fairly quick too. So reactions between two solids are very slow because they can only occur in the interface. So here I've drawn a box around. They can only happen right there. So liquids are a bit faster because the interface is a bit more and they can flow around each other. Okay? So they can intermingle and mix. For a gas, they can definitely intermingle and mix, and they've got a lot of kinetic energy, so the reaction happens all throughout the volume. Okay, let's give names to these. A homogeneous reaction is where all the reactants present in a homogeneous mix are in a homogeneous mixture, such as a solution, gaseous, or aqueous. Okay, so here homogeneous reactions occur throughout the 3D volume. Okay, so they're quite quick. They can happen all throughout three-dimensional space. So factors that influence the rate of reaction in homogeneous reaction is the concentration of the reactants, or how much you have there. If you have a catalyst, and we'll talk more about catalyst next chapter. Sorry, we'll talk more about catalyst later in the chapter. The temperature, And the temperature will help, because temperature, one expression is kinetic energy, or how fast the particles are moving. If the particles are moving faster, they've got less electron-electron repulsion. And mixing to maintain homogeneous or homogeneity, okay? So you don't want products building up on one side and slowing down the reaction. You want to mix them through evenly so they can have a good chance of meeting each other. Okay, let's contrast this. A homogeneous reaction is where all the reactants present in a homogeneous mixture, such as a solution. Oh, oh, I'm quick, aren't I? Look, all I've done is copied it over and showed the endpoint of this reaction. Oh, what a dim. Okay, now we're contrasting it with heterogeneous reactions, okay? It's where the reactants are in different states, okay? So here I've got a liquid meeting a solid, okay? And the reaction can happen here. Here I've got a gas meeting a solid, and the reaction can happen around here. And here I've got, it looks like a liquid and a, well, it has to be different, a liquid and a liquid, so they don't mix, okay? So an immiscible liquids. Okay, so the reaction here takes part at interfaces, or where they meet, instead of all the way through, like in the homogeneous, yeah? So here they just happen on certain surface areas. Factors that affect these, again, the concentration, a catalyst, temperature, mixing as well, but here's the new one, the surface area of the interface, okay? Smaller surface area, less likely collisions that are successful. Larger surface area, more likely you're going to get more successful collisions. Okay? Alright, and here's me just copying it over and showing some reactions happening there. You can see the progress. Okay. I'm going to call it quits here. Next video, rate of reaction.